Thanks. Is design something people are interested in here? I didn't really connect design with cosmologists in my biased understanding. But I'm not going to talk too much about design today. I'm happy to discuss about design. I do research in differentiable physics modeling, and that one is maybe much more relevant for design. And today I'm going to talk about foundation models, which is a different branch of research that I do. So anyway, so if you're interested in design, I think I'm happy to talk about differentiable physics modeling. This is not, again, this one. Okay, so here I decided I'm going to talk about foundation models. And so how many of you know foundation models? Great, sorry. So maybe you guys can maybe sleep in the first half when I discuss what foundation models are. And also I work in, my training is neutron physics or particle physics experiments. So it's maybe also quite different. And so with my talk, probably it's difficult for you to, I'm just guessing. It's probably challenging to think how exactly you're going to apply this technique I'm going to talk about to your research. So again, just come and feel free to talk to me. I'd love to learn about what kind of research you do and how maybe you can apply some machine learning techniques that I know, or maybe I would like to also learn from you. Okay, sorry, it's a very long preface. I work at SLAC. These are students, my current students. They work with, and obviously they do a lot of work. Oh, and also this is the kind of the detector image that I deal with. So this is a imaging detector, and those lines are charged particles that's going through a detector. And so they deposit energy, and we basically detect those deposited energy. And we can either view that either 2D projection images or the natively 3D imaging detector. This one is a natively 3D imaging detector. There are lots of particles. Typically what we are interested in is these. You can see these straight lines, the standalone straight lines. That's background, so we don't care. But we are interested in when, say, for example, some particle comes in, you can see multiple particles coming out from this point, which we call vertex. Just like collider also collide particle at PP and then has the vertex with a bunch of particles coming out. We would like to understand, we want to identify these first one in the image. We want to identify individual particles and analyze those particles' kinematics. So that's the kind of image analysis we do. Okay, so particle imaging detectors being used for more than many decades, right? This is neutron image, neutron interaction. Neutron came from the right-hand side and interacted, and you see these particle trajectories bend because of the magnetic field. And so this technique has been used for, again, many decades. Today, in particle physics, our detectors are really huge, especially for neutron physics, because you have because this neutron physics, neutron interaction is very rare. So this is Super Kamiokande detector. This one's built in 1996, so that's already about 3 decades old. But it's huge, right? There is a person over there in the picture. It's 50,000 tons of pure water and having 11,000 sensors that's looking at photons produced inside this detector. The reason why I'm showing to you this is so it kind of gives you the idea of the imaging space, right? So this is a huge volume we want to image, although the sensors are all on the side, and it's about 11,000 sensors, but it's again, it's 30 years old detector, right? I'm not going to give you the lecture of these detectors. I assume most of us are kind of familiar, and also it's not irrelevant. All it matters, at least for me, for this talk, is for us to share the understanding of what kind of data we're looking at, right? So this is an example of this detector data, and say the one that I showed you, Super Kamiokande, right? The cylinder thing with the 11,000 sensors is this one. You can see each of these dot is that sensor, right? And then here, that detector filled with water detect charged particles producing Cherenkov light. So that makes Cherenkov ring. So in this detector, they detect a particle, right, which may look like line in this detector, but in this detector, they see that as a circle projected on a cylindrical surface, right? And so this one is pretty simple. Just have a single particle projecting single ring. But imagine if it has interactions like this. From this point, multiple particles coming out, right? And if each of them makes a ring, then the rings can be overlap, right? And so it can be a pretty complex data analysis. This is a silicon tracker. This is a Sphinx. It's a heavy ion collider at the RIC. Brookhaven. This is a simulation of Dune detector. It's one of the experiments I work on. It's a liquid argon TPC. This is actually a 3D imaging detector, like the one I showed you in the front page. But this one is just a static 2D projection. This is a 2D projection, a liquid argon TPC. It's same type of detector as this one, except like I said in the beginning, it can also make a 2D projection image. When it's done, this is how the event looks like. And in this pictures, what I want to say is pretty simple, right? It's not just huge detector. These detectors have now millions of sensors, or 10 to the 4 to 10 to the 7 sensors. And so it has a pretty high, very high precision imaging, not just a huge image. So we want to analyze these things, right? But image analysis can be complicated. I want to just maybe first guide through, kind of like set the bar for the kind of challenges that we have with this image analysis. So first of all, this image just enlarged, right, from the previous slide. This is a neutron interaction, neon flavored neutron coming from the right, left. We don't see neutrino, that's a neutral particle, but it interacts with the argon nucleus here and it produces these particles, right? And also there's other particle trajectories which seems to have nothing to do with neutron interaction. And they are actually background, in fact. So when we get this kind of image, right, we want to identify that vertex, but there's a lot more, right? First, we want to identify different particles, and you see that the different geometrical shape. This one is electromagnetic particle. In this case, it's actually a photon, right? So it's an electromagnetic shower. Or if you have a muon, which we call truck-like particle, it makes this kind of straight line. And it can be important, right, because this is such a completely different geometrical shape. And this one is photon, it has some gap from the vertex. If this is an electron shower, it can start from the gap, right? And then that helps us to identify whether a photon or it's an electron. And also if you can identify, right, these EM shower particles, pixels, separately from these, again, truck-like pixels, right, then allows us to find wherever they touch is vertex, right? So that's a useful key information. Even the truck-like particle is not straight line. You can see it can wobble because it can do the multiple corner scattering. And those kinks and wiggles tell us the momentum information for this truck. And those kinks and wiggles you can see right in the macroscopic view right now. But you also want to zoom in because there's actually, so say for example this, right? This is, if you zoom in this box, you see this, and this is a delta ray. It's a knockoff electron from atomic nucleus when this muon goes through. So enough kinetic energy transfer that this atomic electron gets knocked off and you can see its trajectory, right? And it tells you how often this happens, for example, and also the direction of this electron motion tells the direction of the particle, as well as it's a key for the momentum estimation. Same thing, sometimes that track, that one is easy to see. Sometimes it's right, it's in your view projection, so therefore it can overlap with the main trajectory. It can look like just a few pixels of higher energy deposition. I forgot to tell you about yellow and red color and green color is high energy deposition compared to cyan color. And dark blue means there's no energy deposition. Anyone has any question? I kind of speak fast, but I hope it helps to keep you awake. All right, so like I just said, I guess, this color is important. So if I zoom in, for example, focus this trajectory right here, right? If I zoom in this region, it's like cyan color. But then as this particle comes to a stop, some of you, or maybe all of you, I don't mean any offense, probably know something called Bragg peak. So it's a charged particle as it comes to a stop. How much energy deposits as a function of unit length changes, right? So that more energy gets deposited as the particle comes to a stop because your cross-section simply becomes larger. And so this is that if you look at the same track, at the end, you can see, right, it's more yellowish, greenish color. And this is because this particle is coming to stop, so therefore you observe the Bragg peak. I mentioned earlier, this is a photon shower, right? Photon shower, but the photon is neutral. So when I say photon shower, it's just that it means it's induced by photon, but what we actually see is photon pair produce E plus and E minus, right? Electron and positron pair production. And because they are produced at the same point, obviously, because of pair production, and the electron mass is 0.5 MeV, and I forgot to tell you, these particles we're talking about is like hundreds of MeV or GeV scale. So therefore, E plus, E minus are both collimated, right? And so as a result, at the beginning here, if you zoom in, you see actually two electron and positron overlapping. So again, cyan color is a single particle, like right, energy deposition like this. At the beginning, it's yellow and green, and you also see there's two particles coming off like this. Is because at the beginning, this is a photon shower, you see E plus and E minus together. On the other hand, if you just see single electron shower, you do not see this high energy deposition at the beginning. Okay? So when you see this image, you can get the largely lots of information, just, oh, this is a EM shower here, this is a truck here. But if you zoom in, there are lots of microscopic information you can use to infer physics from this image. So that's why I'm saying like the large scale information is important, but also microscopic information is important. So in this image, this is one event display, so it's one event of microvone experiment. And another challenge I want to highlight here is I want you to find neutron interaction in here. So neutron interaction looks like, it can look like that. This is a very obvious neutron interaction you see from the point multiple particles are coming out, right? Okay. Okay, this is actually, I don't try to be evil to you, right? The answer is there's no neutron interaction here. What I wanted to demonstrate is basically when we recode our image or detector image, by the way, this is an accelerator-based neutron experiment. So we know when neutrino beam comes through our detector. And when it comes to our detector, we record this, right? But the point is, about maybe 1 in 200 images we see neutrino. So that means you have to confidently reject other 199 images and say like, oh, there's no neutrino in here, right? But you can see it can be challenging because you have to see everywhere in this image space. And let me overlay some neutrino interactions in actual scale. A huge neutrino interaction will look like this. You can see here, right? This is an interaction vertex. I have 2 particles coming out, right? This one is a very obvious huge neutrino interaction. But I would claim it's not super easy, again, if I don't put the yellow box here, and this thing is overlaid with this bunch of background cosmic ray particles. But it can be also as small as this box right here. And only after you zoom in, you see a single particle.
So is one of those an electron and the other a muon?
This one is a muon neutrino. And so this is a proton track, and this straight line is a muon track. And actually, if I zoom in here, there's also a mixture electron I can tell from here. Thank you for asking questions. Otherwise, I feel like I'm just giving a speech. And I just feel nervous, right? I'm sure you guys feel sleepy and uncomfortable with listening to me. Okay, so I just want to be super quick about the data, because again, I want to set the standards, right? I have some understanding of what kind of challenges we have in data analysis. Again, maybe rephrase challenges, right? Accurate and precise image analysis technique is challenging. Has been the challenge for decades, right? A scalable software for, again, and on top of it, right, not just doing the accurate and precise, but we have to analyze like tens of millions of those images, right? And each image has at least, this microburn is already finished data taking like 5 years ago. So that's an old detector, right? And that thing is already about 100 megapixel every event, and you have about 10 million events, right? And you have to analyze all of those. But in the future, Dune detector is about 1 billion pixel images, and then we have at least like 20 million images to collect, right? So number of pixels again you have to analyze a lot. And the final thing is the imperfect modeling, because some of these techniques with image analysis techniques we develop using simulation. But if simulation has a bias, what are we gonna do, right? Okay, so these are the challenges. You already saw this image. Left-hand side, I thought maybe I put some easy to identify similar images. We're not going to do the neutrino analysis, but I just thought it may be fun. This is, as you just argued, the muon neutrino interaction. So it interacts here. It produces proton and muon. Proton has this yellow color, means that because proton is much heavier, and so it comes to a stop right away, and you see the high energy deposition throughout the track. So again, this color is useful. This is electron neutrino. So when electron neutrino interacts with argon, it can produce proton and electron instead of muon, right? So this is the different flavors in neutrino. So we want to again identify. You can see if I see just 2 tracks, that's no mu. There are a bunch of other cases too, but let's say this is mu interaction. If I see a truck and a shower, that's mu e. So like I said earlier, just being able to tell shower shape versus truck shape is already very useful, right? And it's so clear to you. It's so intuitive. Why do you even need algorithm to do this? Because you can see it right away. But unfortunately, right, again, if I give you this in a huge background image, right, and also if I ask you to scan 10 millions of images, that becomes very difficult. But then we have deep learning, so that's fine, right? So we do use deep learning algorithms for across the analysis. And yeah, so this is one of the work I did 11 years ago by now. So like this is automating the detection of neutrino interaction in this huge image. So I showed you earlier about the image, and I asked you where's neutrino interaction. So this is the kind of thing you can do. This is the box drawn by the algorithm to find like, hey, there's neutrino interaction here, and this is the vertex, this is a new muon interaction. So you can do this kind of object detection. You can also do semantic segmentation. Semantic segmentation is a technical term, jargon. That means we classify different type of particles at the pixel level. So I mentioned you earlier that being able to separate EM shower particles and track-like particle is useful, right? So this one is doing, hey, track-like particle is identified by coloring. This is the input image, right? Coloring in yellow, right, pixels. And then EM shower is identified with the cyan color pixels, right? So this kind of analysis is done, it can be done. By the way, if you're interested, if a muon neutrino came in from the bottom, it interacted right here. And the proton back scatters this way, and the muon goes ahead, and then, but it also, obviously, it scattered off and lost energy a lot, right? That's why it suddenly changed the DDX, right? So again, this is the kind of analysis we want to do. We want to identify, oh, this is not the vertex. this is the vertex because you see proton is stopping this way, right? And here's a little bit of a kink here. And also, if you backtrack this gamma ray back to the direction, the other direction, you find it coincides with this small kink. Same thing for this gamma ray. These two gamma rays are neutral pion decay, right? So you can trace this back to the same point where the small kink exists, and then you'll be confident this is a vertex. And then you also have the muon going here, in this direction. And actually, it's actually quite possible. This is muon. Actually, I don't think so. This is actually maybe charged pion. And that's why I think it actually a hard scatter here from nucleus and keep going. Because this distance, if it's muon and having this level of high charge deposition, I think it's very unlikely. In fact, this might be a charged pion coming here and hard scatter with maybe charge exchange to proton. So it can be very complicated, right? Okay, so my point is, sorry, I got kind of excited to just explain that image, but we're using deep learning to analyze this thing. And it comes to the point of not just like using a single model to do single analysis. In experiment, right, in a collaboration, or in particle physics collaboration, we tend to develop some common analysis framework first, and then you infer physics to some level. And after that, there are a bunch of different physics analysis done using this information by a bunch of different analysis groups. And so,
this is a 3D.
yeah, this one is 3D imaging one.
Yeah, so it's easier than it looks here, right? Because here you
Done 2D?
have projection
Yeah.
in 2D that gives the impression that you could be confusing different kinds
Correct.
of events, right? But in fact, because of your 3D information, you're able to better distinguish between
Correct.
background and real event.
That's correct. That's correct. Maybe if I have time, then if you remind me, I can show you the reason why we also have the 3D imaging detector. And that's because I showed you so far like this one too. Like maybe there are 3 neutrino interactions here, right? The near detector is expected to see about 250 neutrino interactions, or what I do is about another 100 muons coming from the beamline. So imagine this busyness times about 100. So there are 100 times more particles in here. Right, and then you can imagine if we do 2D projections, there's no way we can do that image analysis, right? So that's exactly what you said.
Because astronomers are always facing that projection.
Yeah, I see. Okay, so yeah, so in the experiment, we even make like not just a single deep learning model to do certain analysis. This is an example of a composite model. In fact, this is something I worked on 5 years ago. And it's a data reconstruction. So it's made of multiple CNNs as well as multiple GNNs. And it's a composite model to do the multitask cascade optimization. So that means it's try to infer about maybe 20 physics variables that people use for the analysis. And yeah, so you can chain them together. And in this particular case, we are successful to make them avoid the race condition so that you can do this one-shot optimization for the all of the deep learning models that's together, which is nice because if you don't, those traditional techniques which does not use deep learning model, right? In our field, it's very a typical thing we do is you have maybe 20 algorithm developers. They have different algorithms developed, and then there's a software combiner person who gets this 20 algorithms committed, right, in one day because there's a deadline, and this person has to put together 20 algorithms in a chain because they are different algorithms. It's not doing the same thing. Right? One algorithm depends on another algorithm that depends on another algorithm, and you have about 20 of them. And we see like these developed independently by physicists. Are they going to work together when they commit? They don't, right? So you're going to spend about half a year or even a year. The software combiner person or manager person try to stitch together these algorithms, and they're going to make it run. Is it optimized? Of course not. You just spend half a year, 1 year to make them run. That's it, right? This is nice because, of course, everything works together, but also you can just optimize by just pressing a button, right? Nobody goes in with any manual operations, and all the algorithms against all the reconstruction targets get optimized. So that's nice. It's a full automation. It's also shared across experiments. This algorithm, this software we built is now used by 4 experiments, and there are like about 6 experiments that use the same detector technology. So it's basically being used most of them. But here's the caveat over the same detector type, right? So again, you get argon time processing chamber that makes either 3D image or the 2D image. Our software can handle both of those, right? But nonetheless, it cannot be used for example, a silicon tracker that I showed you earlier, or the water Cherenkov detector that I showed you earlier, right? It's a different, that's not going to handle this. And also this is an interesting thing. I was just asking, I was having this conversation. I asked my friends, cosmologists, and I asked them, is machine learning critical? Like, is machine learning important in your field? Is there something that you cannot deliver physics without machine learning? And I get a mixed answer. Right? Yesterday I got an answer that says, no. Meaning like it's not that important. I mean, it's maybe fun to, it's maybe powerful, but is it like necessary? And then his answer was no. But in this particular case, for example, doing experiments like a $3 billion experiment in the US, right? And then without this, it's not gonna work. Because there's no other alternative method to do data analysis. So mission critical is the point I wanted to say. These deep learning techniques for particle physics imaging detector analysis. Okay, but some challenges remain, and key challenges. So first, no unified analysis backbone. So this is, I mentioned in the previous slide, you can have this, combined deep learning model to do, to serve the experiment, but different analysis can use different software to do this. Meaning, like I said, this is mission critical for the main physics results that Dune experiment is going to deliver. But there are some people who's doing physics analysis that is not main, and they can develop their own AI algorithms, especially because maybe the software I showed you is not suited for them. But that is one example. In general, in particle physics, including LHC colliders, there are lots of AI models, right? So you can see like today, you can invite people to talk about their own AI model, and you ask a question like, do we need all of them? And what does it mean, right? If I have, say, somebody is analyzing mu signal, mu neutron signal, and somebody is analyzing electroneutron signal, and if they use different image classification technique, even if the algorithm, let's say you use the same CNN, right, to do this, maybe let's say you use the exact same training set, right? But if they train them independently with different target, right? Then they do not share, for example, dependence to, say, detector physics process, such as systematic uncertainty estimation, becomes different, right? So when you have, say, 100 different analysis, which is typical in again, particle physics, because our experiment is very expensive. So we want to support many physical analysis, right? And if they use different AI models, how do we consolidate? How do we even make understanding of one analysis against another? Again, that's very important because systematic uncertainty estimation is something common across these physics analysis, or at least there are common parts. And so we have to have some consensus on how you estimate systematic uncertainties. Okay, yeah. So if you can have like one AI model, then that's great. Again, this is not something that I force, but at the same time, right? If you're a physicist, you know how physics works, right? So you don't have to use machine learning, but you can. It doesn't matter. But as a physicist, right? You do the analysis, like the images of the particle I showed you. And it's not like I doubt your analysis, and I have to do your analysis, right? You showed me a set of plots and convinced me, and then what is the physics process you took into account, and you convinced the rest of the collaboration this analysis is legit, right? And this is because we have the shared understanding, right? We have a comprehensive understanding of how particle physics work, how these detectors work, and so therefore we can do the analysis together, or we can share the verifications, and we can move forward for the inference, right? And if these AI models, especially we are these days talking about even like AI scientists, why can't we do the same thing? Or why shouldn't we aim for the same thing? Why don't we have that one AI model that has a comprehensive physics understanding, so therefore you can use for the inference, for the common inference? So that's one challenge. Can we have just one model that has comprehensive understanding? Can we avoid having an AI model that's specific to a certain task? Right? That's what we do when you do supervised learning, right? How about detector and experiment specific thing? I mean, I mentioned the software I just described can be used among liquid argon time projection chambers, cannot be used for the collider, cannot be used for the Bottleneck. Like, why not? Right? Because the images I showed you, for example, the collider one, right? That seems similar. Don't you think? Yeah, this. It's just a bunch of lines, right? If a model can understand how particle trajectory formed in 3D world, why can't I analyze that? Right? And a little bit of stretch, yeah, can I analyze that too? Because this is also, I have just sensor position in 3D space, and if I can generalize this by saying, well, my model understands the geometrical shape, right? And understand the physics behind the geometrical shape. Well, this is a geometrical shape too, right?
But in general, private physics usually use a completely different type of detector together, right? Is that still okay in this case? Because you are usually using a similar homogeneous type of detector, right?
You don't have, yeah, sure, yeah, it's okay. Yeah. You can use different detector.
To mix up different type of detectors.
Yes, yes, yes. I'm not going to talk about it, but I'm happy to discuss with you if you are interested in that direction. But yeah, certainly that's fine. Yeah. The last point is the fact that it's supervised, right? So if my simulation has mismodeling, how do I avoid that bias coming from the mismodeling? Can we train our model on data without labels? So these are 3 questions I try to answer in the next half of my talk. But first, I'm gonna maybe describe foundation models so that we have the same understanding. So I'm not gonna try to tease or anything. So foundation models, I'm gonna describe in the rest of my talk, but can address those 3 challenges I mentioned. So I'm gonna show you how kind of like the recent results. It's just a teasing results that shows promising results to address those 3 questions. But I have to first explain to you what foundation models are. So it's defined in a paper, so you can go look at this paper, right? By Stanford people, which I feel like such a position paper and terrible. But I also get paid by Stanford, so I have to advertise. So foundation models are any model that is trained on broad data, adapted to a wide range of downstream tasks. So it's trained on, say, diverse set of data. What do I mean by diverse? We're gonna talk about it. But nonetheless, as such, once it's trained, it can be used for a bunch of different tasks. Okay, so let's see. So I'm going to use large language models as foundation models because this is where the term foundation model was coined after GPT 2 and 3 came out. So LLM, right, it takes sentence as a sequence of words. So if here's a sentence, my sentence, and then you can see each word is converted into a vector called token. So it's just a bunch of numbers, but it's 1D vector, it's same size, right? Okay. So it's English sentence, every word is converted into a vector of numbers. And then it's going to be processed. So how do we train this LLM? There are many ways to do it. But the very first LLM, and it's still used underneath, the technique is called masked word prediction. And what you do is you mask single word here, right? And the task for the model is the model is given the rest of words and it's empty vector, right? It's actually not exactly empty. But then the model's task is to fill this vector with the right numbers that represent this word red. Okay? And so the model is trained this way with all different kinds of sentences, different kind of masks for different words, right? And so, but if you just focus on this, right? If the model, how the model learns this, how to get this word read, right? First, it has to understand maybe grammar, right? Because there are a set of words that means color, right? And also, it's not a bar. So obviously, it has to learn some grammar, but it learns more than a grammar, right? Because the color of apple, the most common color of apple in this word is not black, right? But sometimes you do see sentence that says yellow or green because those apples exist, right? But typically it's red. So for the model to get this right, the model has to learn the probability distribution behind this word, right? The probability distribution across all words in principle, but in here I'm just showing my guess distribution. I actually don't know if this is correct, but different colors that fits in apple, right? So again, for the model to get this right, it has to learn much more than the grammar. It has to learn about the context, the frequency of which color fits here, right? And that is basically English sentences that's in a huge corpus of data set. And from that, it understands its frequency. It tries to learn the probability distribution behind that describes our word, right? Because those English sentences in the corpus describes our word. Okay, so this way, the model, again, not only learning the English grammars, but it also learns about our word, right? So as a result, to this model, if you ask questions, right, it can answer the questions with common sense. Why? When I say common sense is the part important. It understands the common sense because it's whatever common defined by the dataset and the frequencies in that dataset. Okay, so that's how LLM works. And this technique, now if you just scope out, right? I hope this was clear. Does anyone have a question about this? Okay, so what this technique has achieved, right? This technique is a class of learning technique for self-supervised learning. It's self-supervised. It's supervised because you still have the label, right? It's self-supervised because you produce a label by yourself, right? You didn't need labels to be provided to you. Okay, so that's great because labels dataset is expensive, right? You have to have people label the dataset, or you have to have a 100% correct simulation tool that can provide you with the dataset, with the labels. But this one, it can unlock huge amount of dataset, at least in particle physics. We just keep collecting data, and we can use those dataset to now training, and we don't have to worry about simulation bias. I already mentioned adaptation to many tasks. So this is only possible if you make this a broad dataset, right? In other words, if I do this thing with let's say we're gonna talk about it, but liquid argon TPC images I showed you earlier, right? That kind of model probably won't work outside that domain. But yeah, okay, that's what I wanted to talk about. This is also called representation learning. That's more like the big word. Self-supervised learning is a part of representation learning. And then in this particular case, it's called mask-based self-supervision. And there are many other self-supervised learning techniques. All right. Okay, yeah, so just super quick. This is a simplified view by me on what kind of data I see in the foundation models research for science. One side is called symbolic data set. So this is like a language, math, or representation of particles in particle physics, galaxies in your case, and cosmology, for example, and some kind of useful physical quantities. And what do I mean by symbolic data set? What is the grouping here is individual data entity has a strong semantic information. So remember, like in the previous slide, I showed you the masked word prediction, right? The target for the model to predict an English word obviously has a very well-defined meaning. It can have much more meaning, that's okay, right? But have a very well-defined meaning. On the other hand, sensory data set, right? Sensor level data set, waveforms, 2D, 3D plus or any dimensional point cloud, individual pixel doesn't really carry much information, right? So sensory data set has a extremely low information density. Same thing for the waveform, right? Single ADC doesn't mean anything. And there are foundation models developed for each of these things. And it can be grouped by this. Why? Because this one, for example, mask-based self-supervision works really well. Because again, once you mask one word, right, has a very strong semantic meaning, and the target to learn is very well defined, right? So this one, mask-based self-supervision, is the beginning of the foundation models for the language models, and it still stays as a very relevant thing. On the other hand, sensory data set, like computer vision, right? Self-supervision has struggled a lot in the last almost 10 years. More like maybe 8 years. So in fact, so the class of different types of self-supervision techniques developed in AI research, this one has about 10 times more than that one. Okay, simply because optimization is extremely difficult. Learning meaningful concepts from this low information density data set is extremely difficult. At the same time, this is really the nature of scientific data set, because when we do science, obviously we do not capture physics concept. Right? We just capture some phenomena. We don't know where our physics signal may exist, but we just capture this information and then we infer physics from this. Okay. In future, I'm not going to talk about it, but I am interested in this research of AI scientists, but that kind of stuff has to do both, right? If you want to do the scientific experimental workflow, so experimental discovery pipeline, right? You have to have hypothesis generation, right? And the measurement design, and take the measurement, and now you have to confront the data set. So that means you have to confront the sensory data set, extract the information from that, and then you analyze, you do the modeling, and then you check whether your new model is consistent with, right, more than 100 years of publication physics knowledge, right? And then see if it's a new discovery or this is just a different aspect of the known physics, right? So that kind of analysis requires both comprehension of the knowledge existing already, as well as extracting new information from raw data set. Okay. Oh, if you want them on the right-hand side, sorry, this is just for me in case, I don't know how many of you, right, so familiar and everyday use LLM. So that's me asking LLM, tell me about the how charged particle lose energy in a detector. And yeah, so it's pretty impressive nowadays that they actually get every terms in the equation right. You can even okay. Yeah, you can ask more fun questions, and I think it actually knows much better than I do. Okay, outline. I don't think I have outline. Never mind. Happy Thursday. That's it. Okay. Okay. So I'm going to answer those 3 challenges I mentioned earlier. Well, we want to have a single model, right? That can be a common analysis backbone. We want to be able to see one AI model being able to analyze different kind of detector data sets. And also we want to be able to optimize these AI models purely data-driven manner. Okay, so first, right, I still have to talk about foundation models. Okay, fine. So we talked about foundation models. I told you about self-supervised learning. I haven't told you how you train this thing, right? So here I'm gonna just give you a super high-level overview of how you train. Foundation models training comes in 2 stages. The first stage is pre-training. This is a stage where you train this model to have a general understanding of the data or the word represented by your data. So this is the part I mentioned earlier, self-supervised learning part, right? you get a bunch of images, and then you formulate a task like mask-based self-supervision, and then that foundation model learns to map your data set to some high-level latent space representation that extracts useful information, general information, reusable information from your data. You can do the same thing as the LLM, so mask-based self-supervision. So in this case, you have an image of flamingo, and you mask this portion of the image, and you can ask the model to generate the pixel values in those patch regions. So you can do that kind of stuff for the images too. And in fact, that is one of the first very successful self-supervised technique for computer vision. Like I said, it was very difficult. So it took a few years after large language models for the computer vision people to make that thing work. But that's it. Once you have the pre-training done, the second training stage is fine-tuning. So this is adaptation. So take this general reusable representation. So this should include as much information, if not all information, from the input data, such that you can now train a small neural network, or it doesn't have a neural network, it's up to you, but pick a small neural network to do specific tasks, like track shell separation, semantic segmentation, maybe position and direction reconstruction for particles, identifying the pixels that belong to individual particles, so the particle track reconstruction, right? Particle type identification, or maybe you identify group of particles as an interaction. Right? But these are the downstream tasks, right? And you can have even more, these are more like what I call reconstruction tasks. You can have more higher level analysis tasks as well. Okay? But here we achieve a goal of having a large model that does the backbone, and then the small neural network is to kind of project the information into specific observation axis. Okay, here's a little bit of a teaser. So let's say, this bunch of these images we feed in, right? And like I said, this is that microburn image. This is a neutrino interaction. This is a neutral pion decay. It's a photon shower because there's a gap. It's not electron. And this is one of these is muon, right? This is a muon particle decaying into initial electron. Okay, it's example images. Don't get caught too much by it. The right-hand side, this is just a reminder of how semantic segmentation between track-like particle and shower particle looks like. Right. So this, we used to have deep neural network, the example I showed you earlier. Deep neural network trained using this supervision signal. These are labels produced by, this is actually data, this is actually inference. But imagine something similar from a simulation. That's what we use to supervise train the model, right? Here, this one is showing similar large TPC data set used for the pre-training, okay? And what you see here is every data point in here, imagine that comes from the points in the event display, okay? But then they are colored in different type of particles, okay? And you can see, say for example, track-like particle makes a cluster here, right? And delta ray, that's a local electron, make a cluster here. This green one is a shower-like particle, initial electron, right? So you can see in here, these different type of points are clustered separately. Okay, so separation is achieved. Okay. Now, the point is, so how did I get this? This is not even from the small neural network or fine-tuning. This is simply taking the representation from this representative space, which is a high-dimensional latent space, and we just break down into two axes using t-SNE, which is a dimensionality reduction algorithm, right? And then we maximize the separation by this class, right? So that means you don't need neural network for separation like this. It looks like it can actually do a pretty good job separating these different types of particle already without using fine-tuning even, right? So what I'm trying to demonstrate here is when this representation is really good, right, the well-understood concept can be separated even without a fine-tuning process. And that's natural, right? If I just show this image, maybe to my daughter, so many times, my daughter, if I ask my daughter, hey, can you tell me any pixel that looks like this track here? And probably she will not tell me this. Even if she does not have any understanding of, say, particle physics, she will probably point out this. Right? So, that's how successful pre-training can look like. Right? Again, if pre-training is really good, you don't even need to do fine-tuning. Okay. This is especially for, well, no, I was going to say students and postdocs, but also for senior people, right? Probably students are postdoc thinking, like, I want my supervisor to learn these things, right? So self-supervision techniques, I mentioned this mask-based self-supervision. That's very easy to understand, I hope, right? But there are, and I mentioned that computer vision has a lot more self-supervision techniques to cover. These are really interesting, and you have to know this. If you want to do the self-supervision on images, again, mask-based self-supervision can only work so well. And any cutting-edge techniques are some of these. So I just made a list of the self-supervision techniques that you probably want to learn about. Right? I'm not going to cover these, but this is here as a reference, and maybe I share the slides later. In each of these techniques, I have this one-line description of what it is. And also here, these are the terms you can just Google. So each of these is a paper, so you can Google. So these are the kind of leading papers when these techniques are developed, right? So you can go and read those papers if you're interested. Okay. All right. So I think I set up the stage of my talk by spending 45 minutes. So I described the problem, right, and the kind of challenges that needs to be addressed for the computer vision and deep learning. So 3 challenges I mentioned. I explained how foundation models work. I'm going to now kind of run through some promising results that I mentioned earlier. Okay. So the first one is having a single model as a backbone of doing a bunch of analysis, right? So I'm going to talk about this model called Panda. Of course, I named it. This is a paper if you want to take a look. So Panda is a self-supervised model for the point clouds. It can work with any dimensional point cloud, but typically we try 2, 3, and 3 plus 1. This one is a 3D event display I showed you earlier. So Panda, again, right, maps this input image into some representation space, which I call embed. And then from this, small neural network can map to do different tasks, right? Semantic segmentation, again, track-like particle and shower-like particle separation. Identifying individual particle tracks in this image, right? And also doing the particle ID, right? So it's actually pretty amazing from somebody like me who spent like decade to write algorithm to do this. Nowadays, this is completely automated, right? I just saw this data to Panda. I don't do any supervision, any label or anything, and it comes back, and I can just do like an hour training on a small neural network, and it can identify and group these pixels into different particles. Or the pixels into individual interaction. So in this case, right, the same interaction happens here, so all particles that belong to the same interaction get the same color. Okay. All right, so Panda, I think so this one uses a self-supervision techniques called self-distillation. I'm gonna skip. Please ask questions, then I can spend your 5 minutes to explain this later. But this is not mask-based technique. It's a different type of self-supervision. This is the most important part, but I'm gonna skip because it takes a bit of time. So imagine that self-supervision is done, and then this is now looking at similar thing I showed you earlier. So the Panda's latent space projected in a t-SNE2 axis for different particle types, right? So you can see again, as a reminder, I put some pictures of particles. These are like how the shower looks like, right? And the shower is this photon and electron shower. So you can see this cluster, green and blue is a shower, and you can see those clusters together. Same electron, but not EM shower-like shape, Michaud electron like this, right, is also separated, right? Again, this is not even using small neural network to do classification. This is just projecting the latent space to 2 axes, and you can already do classification. This is delta ray. That's also electron, but just knockoff electron in the middle of the track, right? Again, it's very well separated right here, right? Proton is a high energy position short track, and the muon and the pion are very similar, but muon here that looks like a straight line. So when we see this, right? Again, even before doing the downstream task supervision, this makes us happy, right? Because at least for this representation is learned really well. Okay, so this is semantic segmentation, again, track shower separation, and also delta ray, identify Michaud electrons, so that kind of pixel level classification. Lots of numbers, but I'm not gonna have time to go over. If you're interested, ask me later. What I'm gonna show you here is this is the current state of the art. So algorithm used in the community, in the physics community, right, to do this job, right? As a function, right, and so it shows the performance on y-axis, and this gray dashed line is the state of the art in the community, as a function of amount of data you provide for training. Okay, so the more data you provide, the performance increases, right? And this is the current state of the art, right? The Panda actually can beat the current state of the art with 0.01% of data, which means it's 10 to the 4 times data efficient, right? So if you provide 100,000 images to the supervised train, the current state-of-the-art algorithm, which is a CNN-based, right? Panda can be trained with just 100 images, and you already get 95% accuracy, which is roughly speaking the current state-of-the-art, right? And of course, you give more data, performance gets better. This is not the best performance of Panda, just to be clear. That's in the table, 98.8%. That's well above the current state of the art. It's just not on this plot together. And this is one of Panda that does much better already than the state of the art. You have a question?
Yeah, I was just thinking.
Yeah.
I mean, there must be automated algorithms to do this kind of thing.
What algorithms?
There are automated algorithms to do this
Alternate.
already. Right?
Other algorithms, you mean?
I mean, methods for classifying different events. Obviously, no human can do that. I mean, I'm not really strong.
Sorry.
I imagine in physical physics, you.
So I think I'm maybe misunderstanding your question because I thought you mean there are other algorithms to do this.
Not this kind of standard ones that are applied.
Yeah, this is the standard one.
That's
Yes, that's the current state of the art. Yeah, sorry, I use this jargon sort of state of the art, which means this is the algorithm community uses because it has the best performance. And in fact, we developed these algorithms. Yeah.
So you're saying your algorithm does better? Or,
Way better.
Or just is more efficient?
It does way better. So like I said, this one is roughly speaking, yeah, sorry, I rushed, right? This is the performance. If you go over here, it's roughly speaking 95.5%. Yeah. This is F1 score. It is a metric we use to benchmark this algorithm for the physics performance. Okay, it combines in physics term. We often use purity and efficiency, right? This is like F1 score is a single metric that combines both of these. Let's say, right? Because when you maximize the purity, you can kill the efficiency, right? When you maximize the efficiency, you can kill the purity, right? So F1 is a handy algorithm we use for the classification task to measure both of them. So you cannot just mess up, so you have to do well on both of them. So that's why you use this. For this metric, the current state of the art is 95.5%. And then Panda achieved 98.8%. And this 3.3% sounds small, but that's like, it can translate to say nu mu versus nu classification. I would say the efficiency of about 20%, 30% of signal. So it's significant. Okay, and all of those, you just have to trust me because like, because I have to, right? I don't have time to exactly go over all the details, but yeah. Again, I don't think I have time to really go over. If you know the ARI is a metric used very common for clustering community in the machine learning. Panoptic segmentation, so in deep learning community to do the clustering, same thing, the panoptic quality score. But if you don't know, I apologize. That's the metric we use for different particles. But yeah, let's just look at the event display, which is very qualitative, so I apologize. As a scientist, we should be quantitative. But you can see, well, okay, so many particles, it's very difficult to see. But if you look at letter, it agrees very well. It's hard to see, but there's actually letter mu here, so mu1, and here's an electron, right? You can see here, this is a mu1, letter mu1, and here's an electron, right? You can see pretty much every small delta ray in this image is identified by the algorithm as well. And yeah, this is way better than, again, the algorithm that we wrote 10 years ago. This is, what is this? This is vertex and angular resolution. Okay, I'm not gonna go into this, sorry, because we don't have time. This is interaction clustering. So again, grouping pixels into interactions, not individual particles. Right? Interaction is made of multiple particles. Right? So this even display particularly, it kind of looks empty, but it's kind of amazing. Is you can see here 2 particles struck right, green color. This is truth, right? This is the right answer. And you can see this yellow one. This is the accidental cosmic ray muon. It just happened to go right next to it. But you can see here that is not confused as well. And yeah, so this is obviously, this one is just the one that I thought interesting to pick it up. And so if you don't trust me, you actually have to look at the score numbers. This one is competitive. It's not quite like much better. Okay, so that's challenge 1, having one backbone algorithm. And I showed you all different kind of metrics. Those are all different downstream tasks that's performed using the common learned representation by pre-training, right? Largely on data. But fine-tuning part did use simulation. So we're gonna go back to that point later. Okay, challenge number 2. Can we have a single model that analyze different kind of detectors, right? In particular, what a Cherenkov detector, because my friend, my very close friend, work on these things, and he's, they want to resolve something, as well as this like a silicon tracker with magnetic field. Okay, so what a Cherenkov detector? I mean, the image I showed you earlier, I told you this looks very clean, but then the problems they want to solve is image like this, where that's the energy deposition image. So this is the data, and this is the result they want to get. This one, it shows different color is assigned to different particle. So this is a multi-ring event, right? In the water Cherenkov community, right, water Cherenkov detector, Japanese people have been using for neutrino physics for like basically like more than very long time, right? But Kajita-san, I believe, is one of the people who actually wrote the reconstruction algorithm, right? And that's not what he got Nobel Prize for. That's definitely one thing people remember him for. And since then, nothing really changed, right? They still struggle to do multi-ring analysis. They can do a single ring analysis, but multi-ring is very difficult. So events like this, if you can address, then that opens up a lot more data they can use, because you can manage a lot of data set that has multi-ring in it. So again, I want to, and we actually have the results for a bunch of different downstream tasks, but maybe I will just focus on doing a multi-ring analysis. So yeah, this is t-SNP plot. We already saw it so many times, so I don't care. Okay, so this is a terrible plot, but it shows kind of promise. So maybe look at the table first. Focus on this slide, please. I understand that we want to look at this, but let's look at this one. This is the current state-of-the-art algorithm in the water Cherenkov community. It's showing you how much fraction of true one ring, right, you can reconstruct as one ring, right? So true one ring event display. Can I reconstruct this one ring? 95% times yes. Sometimes 4.6%, this algorithm reconstruct this as two ring, so it's a misunderstanding. And sometimes one ring is broken down to more than three rings, equal or more than three rings, okay? And if you have two rings in the image, like I said, then by default, they do not really use for physics analysis, but nonetheless, you can try to do this reconstruction, right? Two ring, about 30% seen as one ring by this algorithm, so cannot resolve. 66%, about 2/3, correctly recognized as two rings, right? And about 5% more than three rings, right? If you have three rings, then 7% one ring, interpret as one ring, 25% two rings, and about 67% three rings, right? This is like super preliminary results, but it shows you normalized on this axis. True number of rings is shown in the vertical axis, and reconstructed number of rings on the x-axis. So for one ring event, it's about 90%, it's correctly recognized, and then 95%, and then 56%. So three rings, yes. So three rings is not better than this, but two ring analysis can do much better. This is super preliminary, right? This state-of-the-art algorithm is trained with, is optimized with hundreds of thousands of images. This one, ours, is only optimized with about 10K images, because this is just something that we tried a few weeks ago, and we're actually rather surprised that it can do multi-reconstruction well. So this is actually randomly picked images. This is the example of three, but randomly picked more than one ring images, right? This is the truth. That's the charge image, that's the event display. Truth. And this is the reconstruction. You can see it's pretty difficult, right? Somehow in here, you have to, your job is to color these pixels to find 1, 2, and 3 big rings. And there are very small, say purple color doesn't really make a ring, right? But that's also a particle. On this side, you can see the blue ring, right? And a green ring, and then orange ring as well. And this is, I mean, I almost don't understand like how the algorithm is doing it, because as a human, if I look at this on the left-hand side, I cannot do this coloring. All right. So it looks quite promising, so we're gonna keep optimizing this, and hopefully it will achieve a lot better result. But yeah, water Cherenkov community people, like hyper-K people, hyper-Kamiokande people are extremely interested, so we started working on developing analysis using this already. President must speak. Yeah. Too much. I don't have time. I think I'm already pretty much done. However, we should ask for the questions. I'm gonna maybe talk about, sorry. Oh, this is Sphinx. So Sphinx also works pretty well, but obviously I don't have time, so I'm not gonna talk about the details. So yeah, we can do the Sphinx. This is the clustering of the pixels or the track points into individual particles and doing the PID. And it performs actually better than the foundation model that Sphinx collaboration developed. So that's something we're writing a paper about. But okay, let's move on to the third one, data-driven fine-tuning. Okay, so we have this scheme, right? Input data, use foundation model to transform into representation space, and you have multiple small neural network to do physics inference, right? What if we will run forward simulation? Well, this is inferred physics information. So we can run the forward simulation to make inferred data or simulated data set, right? Given this physics, if this is accurate, and if our physics modeling here is also accurate, then these two images should match. Does that make sense? And if this simulator is differentiable, and I mentioned to you earlier that the foundation model is like 1/3 of my research, right? Another 1/3 of my research is differentiable physics modeling. And so we have developed this Water-Cherenkov, but also other detector types, differentiable full detector simulation, so that if you give us this list of particles, we can model and then generate this image without using any surrogate or emulator or generative AI model. This is the exact physics model, right? But we turned that into differentiable algorithm. So because it's differentiable, the difference between those two, right, can be quantified, and we can optimize these algorithms to output reconstruction output or the physics inference output such that it respects physics and maximize the likelihood because this has to look like data. Okay? Now if you do this, right, this is nice because now you no longer need a hard label. I don't need to train with vertex or particle type, right? None of these things, right? This simulator process does come in to enforce implicitly the physics process or the detector, right? But I don't have to, again, give the hard labels or particle type that comes from the generator because in neutrino physics, neutrino event generator, nobody trusts, right? We don't want to rely on that at all. So what kind of generator, physics generator can you use to make events in the simulation to train a supervised model? We never had an answer. But this way, you can actually use real data, right? And you can sample from a real data distribution to learn and enforce these, again, physics models to output information which follows your physics prior knowledge for your detector physics, right? Not the generator physics.
So not fully understand. So what you do here is that you have data.
Yep.
And you then get a model and you kind of recombine this model data into physics particle type, and then we refit those data to fill these particles back to the kind of simulation, and then you compare the data. Right? It's a data comparison. It's not exactly the particle level, but compared as sensor level. This is what you think, right?
Yeah, comparison at the sensor level.
Oh, okay.
Yeah, comparison. So this is where the loss is defined, right? We compare our inferred images of the ring, which assumes your reconstruction output, right? If this is wrong, that's going to be terrible, right? But that's going to be informed through this loss function, right? To inform these guys, hey, you have to change your perception. Otherwise, right, your likelihood is terrible, right? This is nice because typically we measure data simulation discrepancies using a physics parameters, right? Right, but it's just summary statistics, right? We can do that too, but in here, we are just comparing the full information at the detector level. And we literally minimizing the data simulation discrepancies at the detector level. Okay, I'm already over time, so I'm just show you two plots to just prove. This is the vertex reconstruction, the particle start portion reconstruction. And it's comparing blue line. This is if I give full supervision, assuming my generator is correct, right? So I use full simulation. And then if I do full supervision model, which of course has a very good result, then you can achieve this vertex error, so this distance of the vertex from the true position to reconstructed position, y-axis, right? X-axis, I'm sorry, I should have described. Y-axis is a metric, and x-axis is the number of iteration to train a model, right? The dashed line here is the performance we achieve after training a long time, supervised model, right? Orange one is the vertex error going down. It's probably actually keep going down even more, but we stop here to 50K for this spot. So you can see, right, it's asymptotic achieving the value that's very close to the supervision version. Right hand side, very complex. If you have questions, I'm happy to discuss. That's more looking at latent space. It's actually a super interesting problem right hand side, but I'm going to skip. This is the same thing for the vertex resolution. Vertex L1 error, so just a difference of the two versus reconstructed direction. Again, supervised signal, green dash line, and then this orange one is not using a label, right? It's not using an angle as an answer, but we just running a bunch of forward and then compare the ring images, and then see if the inference produced the consistent particle information, in this case direction, to match the ring image from the original data. Okay. If this kind of research is interesting to you, we're not doing this like as a siloed research, or like we only care about these detectors. We actually, whenever there's a public data set, we jump on this data set. And we also organize an effort to collect this data set, generate this bunch of data set, and ask this more like a pure AI question, right? The thing is, I didn't maybe mention this, but you can see industries will keep developing better LLMs and better agentic workflows. If we develop those research products, we probably cannot compete. And I don't think there's no point to compete. If they're going to do it, great, we're going to use them, right? But this kind of like, can we learn representations from sensor level data? They're not going to do it because first of all, they don't have data, and they can also give them data. But also, it's very niche, right? If you can find physics from liquid argon TPC images, how is that useful for society? How is that useful to make product? And also, if you really want to, again, demonstrate this actually works, your domain knowledge is crucial because you are the one who knows how it's supposed to work, and you're going to have a bunch of downstream tasks and well-defined metrics to demonstrate that representation is well learned, right? So domain scientists have to do this kind of research of the foundation models, again, on your sensor data set. And so, again, that's why I think it's important that as a community to work together, right? Again, and also because it has a unique domain aspect, right? The techniques developed outside doesn't necessarily work out of the box. I mean, we tried a bunch of different things in a computer vision, and many things don't work, right? And after we have lots of tweaks and additional algorithms, additional regularization, we could make the Panda work. And so again, if we develop this knowledge, then I think obviously it makes sense to share. And then most of these techniques that is, again, uniquely we identified, again, uniquely away from the industry, right? It's still computer vision type knowledge, which means if you have data set that's similar, I mean, if you think your data set, some features can be learned from geometrical shapes, right? Likely our self-supervision techniques research can be shared. So if you're interested in, I'm not reading this slide, but we're making this kind of, like, we have some collaborative effort, right, across experiments, across frontiers to develop these kind of foundation models. We're not trying to invade foundation model for everybody, but we are purely interested in just AI aspect of research. How can we learn automatically from data? Because that's really cool in future if you want to do AI scientists, right? The robot, we want to have a robot that is able to understand data, not just a supervised learning, right? Because you want to identify new physics, and new physics don't exist in your supervised data set. Right? That's what humans can do, right? When I see weird kink in the particle trajectories, right? And it did happen in the imaging detector history, even like 5 years ago or so, a profession like Argonaut, using LRTPC, found this very weird, we call hammer events. Two protons go 180 degrees, and then it goes straight. And it's always like that. There's a peak of the cross section for that to happen, right? And again, that's because physicists keep looking at these images, like, I think this is really peculiar, exactly 180 degrees in all projection angles. And that kind of stuff, right? You'll be able to find, because you are always looking at it and you're learning from data, right? The model that is just trained and only doing the inference is not gonna learn, right? It only does the inference. So that's what I'm saying. Like, I think we want to have self-supervision technique. If you have this technique developed, the model can keep learning as it processes more and more data. Don't worry about this slide. This slide is agentic workflow is also something we do under DOE stuff, but it's not too important. Okay, so I hope I addressed, I hope it was fun to discuss about these kind of three questions we have. Like, can we have one model as a common analysis backbone? Can we have a cross-experimental, AI model that can be shared? Can we have a purely data-driven optimization, which is actually not quite right, because we still use the simulation pipeline for the inference, but without labels, right? Yeah, so I'm excited about this kind of topic because I think ultimately it goes toward AI scientists, which will accelerate physics discovery. Okay, so I'm so sorry I went 5 minutes over time, but I'm done. Yeah, let me show you the clean one. So, or if you want to go for a particular, yeah, this one's good. Okay.
So, I was wondering which one comes first in the process here, because you showed in one of the slides before you showed there was an LLM side, and then there's the technical side as well.
Can you repeat one more time?
So here in this case, like how does the workflow work? First you would have the detector images. The detector images must create this kind of clustering map.
Right.
This means someone has to go through all of them and classify them based on the...
So detector image, left-hand side, goes to the foundation model, which I call feature encoder, right? So this transforms detector image into latent space, let's say 512 features per point. Latent space. So in this latent space, every single point here is mapped to a point in a latent space. Every single point here, this image, for example, has x, y, z, and energy. So only 4 variables. In here, you have, I'm making it up, but let's say 512 variables per point. Okay, so that's the representation here. And then you know t-SNE. Do you know t-SNE? TS?
No.
Okay. So you know PCA. Yeah. So it's a dimension reduction techniques, right? And PCA, you can use PCA to reduce the dimensions, right? So t-SNE is just another dimension reduction techniques where I can assign for each point, right? This class, because I do have in the simulation which class, which point means which class, right? And then I can ask t-SNE to find 2 representation axes such that it maximizes the separation of these, right? So in here, you can see, but again, in this process, all you do is just throw away these variables, right? And then, and that's what I mean. You can actually find 2 dimensions where this separation is very clear. And so this is only possible again if the model has learned some concepts that's very relevant for distinguishing these different classes.
Maybe just a minor one here.
Yeah.
What if the algorithm doesn't know?
Oh, that's a great suggestion. I should.
The reason is because
Yeah.
in our case,
Yeah.
for example, image artifacts, oftentimes we don't know what kind of artifact we're going to get.
Yeah. Yeah.
We may know a subset of the artifacts we have, but in some cases we don't.
Yeah, but I think in that case, don't you want to look for like an anomaly,
Yeah.
right? So the anomaly detection, I wouldn't do this, right? Because this one is like if I know the classes already. I mean, you can look for some weird structure here, but I think that's extremely difficult to associate, right? And in here also, like if you have something that's by definition has to be in that class, right? But you can do anomaly detection in a latent space, right? In this space with 512 variables, of course, but you can find clustering algorithm to find different groups or find any particular variables that is different from other variables. So, I mentioned the later. We're gonna do we also doing the research about agentic workflow, right? Our agentic workflow. The reason why our group does it is because we can couple with this learned latent space from sensor foundation models, and that has a power of not only understanding the known physics, extracting known physics, but also identifying something that is purely learned from data, right? That separates as a feature. And but probably 99% not new physics. It's just a detector malfunction. But it is useful. Any other question? Yes.
Yeah, I have some related question which I was about to ask the same thing, but actually the other way around. So once you have a detector issues, how can you propagate back to your sensor level model? Will be a problem, or how do you deal with that?
Yeah, that's a great question because there's a different level of information. Right, in this case, I need pixels to see as a pixel in here, right? And then for example, say one case, a detector anomaly, and we can identify, say, the time period. If it's time period, then it's going to be set of images that gets affected, right? So then you have some prior knowledge about, okay, well, how the pixels in these images look like in this space, right? So you can do that. But I think something that I want to say is typically I think when we have, let's see. So for example, I might ask more particular specific question like, hey, during this period, my maybe electric field was not set right. So therefore the particle trajectory gets distorted, okay? Then I would probably personally think about automatic TPC, right? For example, I'm gonna maybe look at cosmic muons because those are the samples of straight lines. So if I see the distortion, that's much easier to analyze than EM showers. EM shower has already a branching shape, so therefore distortion is harder to see, right? Then in that case, I might actually do the reconstruction of identifying individual muon particles, right? And then cast that grouping of pixels back to original input, right? And then that actually is helpful because I can already group the points in this space, right? Individual particle instance. And I can look at the anomaly as a set of points instead of individual points. So what I'm trying to say is I think depending on the diagnosis you have, right? You might want to do another level of analysis to group points, right? And then you might, if you don't mind training a small neural network, you might want to do, right, training a small neural network that analyzes information as a unit of particle rather than points. okay, or a unit of interaction rather than particles, right? But I think this really depends on the case by case.
So it sounds like you do like alignment or the calibration earlier before feeding everything in, right? This is what you meant. You have a separate, you can change separate the system to do alignment.
Yeah, I think so. I mean, you can
kind of a fix.
Yeah.
Detector fixing.
Yeah, that's what I understood in your question. Like I said, you opposite between like you start from the known problem and you want to go look into how that represents in this space, right? So that's why I introduced the idea of, oh, can we actually first maybe use some inductive bias domain knowledge to group the points, right? That makes sense for probing the problem in a latent space, because otherwise you have to look at every single point, which may be not very efficient. But also. Yeah, I mean, there's a really interesting idea of, instead of doing like point level classification, can we actually group these data points by different physics concepts, such as maybe those points that is distorted by the distorted electric field versus other points, right? To look for detector anomaly that we just discussed about. And can we automate this process? Because obviously humans, as a human, we don't want to type this in algorithm to do clustering and stuff. Can we actually automate this process using, again, agentic workflow and stuff like that? The nice thing about agentic workflow is it can, as long as you don't mind spending electricity, it can scale, right? Humans, is there only so much analysis we can do, but agentic workflow can actually do many analysis, right, in parallel. So you can find really weird types of clustering done in this representational space, and then try to, again, even analyze that against the detector anomaly from the log of the detector operations, right? That kind of stuff, again, as a human, oh yeah, we can do that, but obviously that's so inefficient, it takes so much time, so I'm not gonna do it, right? But then these days, there's a solution to it, which I think is very interesting to explore. What information is captured by these kind of techniques.
Yeah, the boundary of this color is
Yeah.
so small here. I feel the neural network is not identifying the category according to this diagram. This is for human visualization.
Okay. So,
I have another question.
okay.
So you have a slide compare Panda with non-supervised models.
Oops.
Yeah.
Okay.
So somehow it appears to me that Panda has a limitation for accuracy for 0.98, but in the other way it goes black. Can goes better if you even more data. What's the main difference?
Yeah. So yeah. Sorry. This is the point. I apologize for the plot. The actual Panda best performance is this, 98.8, right? So that, and if you actually look at 98.8 somewhere around here, right? It's better than this.
Okay.
I just didn't plot this best performance. That's why I apologize. This one is actually exploring different configurations, right? And not the best configuration, which is in the table. And the reason why is because we're just exploring these two different configurations, not the best one, but it's still a bit better than the state of the art, this one. And that's why I picked this plot, and I didn't ask my French student to remake this plot. This one, if you care, this is a fully supervised training, but using the Panda architecture. So this one is using CNN architecture, which, like I said, the community's best performance model. But that's something that we developed like about 10 years ago, so we're using a sparse CNN. This one is Panda backbone, but do not use any self-supervision, just supervised training from scratch, okay? And again, these are two not best configurations, but I was comparing against this one, and so this is really a noise here. And if you want to look at the best performing Panda, which has a slope that basically looks like a little bit go above and it goes right here.
Well, but this may also tell that with the backbone training, maybe the fine-tuning is not so critical. You already start with pretty good accuracy.
Fine-tuning is so yeah, here. Yeah, so that's another thing, like you just have to, I'm really sorry. But you have to kind of trust me, right? That difference of 95% to 98.8 or 98% even, right? That 3% difference in this task, like translates to difference in the signal versus background discrimination at the final analysis of like 30% level. So you basically lose 30% of your signal if you use 95% model, right? That 3% is really huge. Now, that being said, I think if I just guess what I think you're raising, and I think others also see it, is, hey, I mean, that's great. I mean, Panda beats this at this level, but you only gain so much, this 3%. And I'm arguing this is a huge 3%, but nonetheless, right, the Panda is extremely data efficient. really the learning is pretty much done around here. Right? I mean, because even the best one, it starts going up at the beginning, but it's basically plateaued around here. So you don't really need the full data set to achieve this point. And this is something very, fairly common for this self-distillation, this self-biased technique I mentioned, right, used. And also again, mask-based model too. We have a paper on mask-based model as well. This computer vision, self-supervision techniques is interestingly extremely data efficient. And data efficient means you don't actually gain too much. You're plateauing pretty quickly after you do the self-supervised training compared to, like, say, language models, for example. And so that is a very different nature. Now, at the same time, I should also warn that we should not take this and say, like, okay, Kazu said this is a very data efficient, that this is what we believe. Language models, right? The computer vision models, it seems to depend a lot on your hyperparameter optimization at different data statistics quite a bit. And so that means if we want to really probe the scalability as a data statistics, we actually have to spend more time, or more compute time, and more study at each data point by optimizing hyperparameter at each point. Right now, in this plot we made by optimizing hyperparameters, I think for this point, right? And then use it like this. Actually, no. I think we actually use it this point. But not small, not that one, but here. And then we just use a fixed hyperparameter, right? And then probe how it scales. But like I said, that kind of stuff can work on symbolic dataset foundation models. But for the computer vision, this is a known thing that you have the data efficiency is high, but nonetheless you actually have to do the hyperparameter optimization at every single data statistics. And that's quite annoying. It limits people's doing the scalability study for foundation models. Because scalability, I didn't mention it, but it's a very prominent feature of foundation models is how it scales and how predictable the performance is as a function of data statistics and compute statistics. Yes?
You mentioned that we should trust you, right?
Oh!
So what
I apologize for it.
Obviously this experiment that you're modeling,
Yeah.
it must be measuring something that's, probably quite difficult to measure, something marginal.
Oh.
So if you apply your algorithm to all of that data,
Yeah.
wouldn't you be able to then,
You mean the final physics?
completely convince us by finding an estimate of something that's more accurate?
I mean, convince. It's full.
Well, you're saying that your algorithm
Yeah.
is actually leading to a much higher signal to noise.
That's right.
Right. That signal to noise is a measurement of something, presumably in this experiment.
Yeah.
So can't you go in this, presumably all this stuff is archived, and
Yes.
apply your algorithm and show us that you're doing better?
Yes, we can. But yeah, we can. But I mean, at least our group is positioned as focusing on this techniques development. It is important to the physics impact as well. We realize that any tools is useless unless you actually make physics impact. But we are working with collaboration. So right now, I mentioned earlier about this the chain deep learning model, right? I showed you as a current how we do things. These multiple CNN and GNN things. This software called Spine, having it's 1, 2, 3, 4, 5 CNN and 2, actually I think 3 or 4 GNNs. We basically developed this. This was, I don't know if you know this thing, but the Early Career Award is a DOE award in the US. It gives me money to do research. And this was my Early Career Award project. We finished in 2020, right? And after that, so basically 2020, I was basically giving this kind of pitch talk, right? And then it just takes a long time for the experiment to adapt, right? But then that's why now it's getting adopted, and it's being adopted. Right? Like I said, the Dune, right, near detector, this is the only reconstruction technique. Short baseline neutron program, I don't know if you have heard about it, but that's an ongoing liquid argon TPC experiment in the US. Right, this is a leading algorithm to the reconstruction in both detectors, right? But it takes like years for experiments to adapt, right? And this is not about proving, it's more about really like, we just have to, for example, this thing is supervised. You have to tune the simulation software. Who's not tune the simulation software? I'm gonna complain a little bit. Basically nobody. So then our group member have to go and tune those things, right? But then so in the last 10 years, I would say, or last, I guess 6 years after 2020, we have been trying to develop across experiments. You cannot just keep requesting things. You have to provide the human resources to get your simulation, sorted, get your detector calibration done, understand your signal response, understand your electronics response, okay? And this is how you do it. So we have been guiding in individual experiment collaboration how to do this because they keep saying that, oh, we want to use this, we want to use it. Oh, okay, go ahead and use it, but you gotta work on these things to make it work. I mean, we cannot do AI development and implementation on every single experiment because we work with 5 experiments. And each experiment collaboration asks us, how can we do this? So we actually hire, or we get like a few students or postdocs, right? Volunteer to a reconstruction analysis group from the experiment. And then we try to train them. We try not to do by ourselves because if we do it by ourselves, they will accustomed to it. It happened before, right? Then we have to do the analysis for every experiment. Does that make sense? That we work with them, but they have to provide the human resources to implement this, and we, of course, support and help that getting the physics impact. Because again, without that, there's no point of developing these tools. But yeah, my talk right now is more like a cutting edge part of foundation models research. It's like talking about this software about 6 years ago. And so I expect that to come out. But I think, again, hopefully, maybe you can invite me again in a year or two, and we can have some results. The reason why I think this time is only a year or two is because it basically established that machinery and the pipeline, right, the collaboration with each experiment, to how to implement this kind of machine learning tools, right? So that hopefully, again, this software is developed by us, and we developed that pipeline. So now we should be able to just swap this with a better version of algorithm and then see the physics impact. But that pipeline is something, like I said, it's still kind of being developed.
And I think we can first finish the talk, and he's around for 2 days. So if you have any questions, you can email him.
Yeah, I can also talk in person too. I'll be in the next building, basically. Thank you very much.